Hello. I wanted to do a little quick video on some of the concepts from chapter 3, just because I thought if you need a little bit of extra guidance on concepts from chapter 3, I can do a quick overview of those concepts. So chapter 3 is focused on falling objects and projectile motion. So let me share my screen to just kind of help us get started, and I'm going to just share a blank screen so that I can write on it. So I'll bring up the whiteboard. The first few chapters of physics are usually focused on describing the motion of an object. We haven't talked about why the object moves that way. We're just describing it. So we could know its initial velocity, its final velocity, its acceleration, the time that it's in motion. We can talk about the distance that the object moves. And in chapter 2, you learned how to connect all of those different variables together using kinematics equations. And the kinematics equations that are most often used is V final equals V naught. When you see a little V0 here, it means the initial velocity, or V naught, plus AT, where A stands for the acceleration and T stands for the time. In the book, I think that they don't put the F here for final, but I just like to put it there to remind us. And the other equation that the book gives us that can describe the motion of an object is D equals V initial times time plus 1/2 AT squared, where D is the distance that the object moves, V naught is the initial velocity, T is time, and acceleration, A is acceleration. Where these equations come from involve calculus, so we do not derive where they come from in this class, but these are two of the kinematics equations that are used most often to describe motion. And these equations can only be used, so these two equations can only be used when the acceleration is constant and it's not changing with time. So the acceleration could be 0. Maybe you're not accelerating at all, you're just moving at a constant rate. Acceleration could be 10 meters per second squared. Acceleration could be negative. Maybe you're slowing down. Acceleration could be -5 meters per second squared, but it's not changing with time. Okay. So those are the two equations that are called, this is two of the kinematics equations that can be used to describe motion. And those you learned about in chapter 2. Chapter 3 is still applying these two equations to describe the motion of an object, except now the object is falling and it's under the influence of gravity. So we're just going to apply these two equations to an object that is accelerating under the influence of gravity. So let's think about the simplest case first. Okay. Let's just suppose I drop an object from the top of a building. Now the object is moving in the vertical direction or the y direction, up and down. Okay. And chapter 3 reminds us that the acceleration due to gravity is 9.8 meters per second squared down. Okay. So it's still moving in one dimension. It's only moving up and down, right? It's not in the two-dimensional motion yet. We're not in projectile motion yet. It's still only moving in one dimension. And let's suppose for the simplest case, this thing starts from rest. So I drop it from a tall building and it starts from rest. So its initial velocity is 0 meters per second. As soon as that object leaves my hand, the only acceleration that it is experiencing is the acceleration due to gravity. Okay, so the acceleration due to gravity, the book, um, the book uses 10. Okay, it's 10 meters per second squared. Okay. So every second, the object changes its velocity by 10 meters per second when you're in free fall. Okay. And acceleration is a vector, so we need to denote the direction of the acceleration. It's directly down, so we'll put a negative sign here, negative 10 meters per second squared. Let's see what happens after 2 seconds of falling. Okay. It's obviously moving faster. And by the way, we are ignoring air resistance here. The only force that is acting on this object is the force of gravity. So the only acceleration it has is the acceleration due to gravity. This is also sometimes noted in books as g, okay, little g. Okay. But it's basically the same thing as an acceleration, and it's negative 10 meters per second squared. We're ignoring any other acceleration on this object due to air resistance and things like that. Let's think about what happens after 2 seconds of falling. So let's say at t equals 2 seconds, what is the final velocity of this object? Well, we can apply the kinematics equation here because the acceleration is constant. It's downwards at 10 meters per second squared. So I am free to apply the kinematics equations I used in chapter 2 to this situation. So V final is equal to V initial plus AT. The initial velocity was 0. The acceleration is negative 10 meters per second every second. That's why I have a meter per second squared here. And time is 2 seconds. So the final velocity after 2 seconds of falling is negative 20 meters per second. Makes sense because that's what the acceleration tells us that it has to be. Every second, the object gains another 10 meters per second of velocity. What is the negative sign telling us here? The negative sign here is telling us that the velocity is going down. So the negative sign indicates downward motion. In the homework questions, they might ask you for the magnitude of the velocity and the direction. The magnitude of the velocity would be just the number, right? It doesn't take into account the direction. So if it was asking for the magnitude of the velocity, it would be 20 meters per second, and its direction would be down. And now let's think about how far the object has fallen. What is the distance that the object has fallen? Again, let's apply the second kinematic equation. Distance that the object has traveled is v initial times t plus 1/2 at squared. The initial velocity is 0, so this first term is gone. Then I have 1/2 negative 10 meters per second squared is the acceleration, and the time is 2 seconds. So this gives me negative 10 meters. Again, the negative sign here just indicating that the object has moved down a distance of 10 meters. You could apply the same thing if the object was thrown upward initially off the building, right? If the object was thrown upward initially, you can imagine that it would go up, reach a high point, and then slow down, and then turn around and start falling down again. In that case, you would have an initial velocity that was positive because the object is being thrown upward with an initial upward velocity. Let's just call it 1 meter per second. And you could apply the kinematics equations just like we did in the first part. Now, there is a period of time here while the object is moving upward where your final velocity, if you were to solve for your final velocity, it would be positive because it would still be moving upward. Okay. If you wanted to know the time it takes for the object to reach its maximum height above the top of the building, at its peak, at its maximum height, the velocity of the object is zero. It stops momentarily and then begins to fall back down towards the Earth. So at the peak, the final velocity is zero. So at max height above the ground, the final velocity, okay, my cat just walked onto my desk. Sorry about that. Sorry. Let me get myself together here. Okay, at maximum height, V final is zero. So you could actually solve for the time it takes for the object to reach maximum height using the first equation. V final equals V initial plus AT. I know the final velocity, I know the initial velocity, and I know the acceleration. And I can solve for the time it takes for me to reach the maximum height, its peak. If I do a little bit of rearranging here, time is equal to V final minus V initial divided by acceleration. That's just a little bit of algebra. Final velocity is zero. Initial velocity, we just called it 1 meter per second. And the acceleration here, it's still under the influence of gravity, so the acceleration is still equal to the g negative 10 meters per second squared. So I've got a negative 1 on the top. 0 minus 1 is negative 1. I got a negative 10 on the bottom. So my negatives are going to cancel out, which is good because I shouldn't get a negative sign for the time. So 1 divided by 10, that's going to be 0.1 seconds. That's the time it takes for, as soon as the ball leaves my hand, for it to reach its maximum height. And then you could also solve for what is the maximum height above the building using the second one and solve for D, because now you know time. So that's kind of free fall in one dimension. By free fall, I mean as soon as I throw an object, as soon as that object leaves my hand, it's now in free fall. The only acceleration it's experiencing is the acceleration due to gravity. And it doesn't matter if I throw it up, if I throw it down, if I throw it, on an angle. As soon as that object leaves my hand, we ignore the air resistance, and the only force that's acting on that object is the force of gravity. Therefore, the only acceleration is the acceleration due to gravity. If And by the way, one more thing. If instead of throwing the ball upwards, we would have thrown the ball straight down, what would we have done? Well, we would have then have an initial velocity. So throwing the ball down. In that case, we would have to denote the initial velocity with a negative sign. V initial is negative. And then apply your kinematics equations from there. Okay. So that's kind of applying the kinematics equation for an object in free fall moving in one dimension. Okay. But what happens once I apply this in two dimensions? Now, what does that involve? I'm going to keep the kinematics equations up here because we're still going to apply them. Let's think about the simplest case of an object moving in two dimension. A ball that's rolling on a horizontal table and leaves the edge of the table. And then it just kind of gradually moves down like this and hits the ground. This object is now moving in two dimensions. It's moving horizontally in the x direction, and it's also moving vertically downward in the y direction. So we have to think about looking at both of those directions. The nice thing is that we can do it separately. Okay? So if I only look at the motion of the object in the x direction, the horizontal direction, the ball leaves the edge of the table and starts to fly off, right? Horizontally, the ball is not accelerating horizontally. Okay? There is nothing pushing the ball forward horizontally to make it accelerate that way. There is nothing pushing backwards on the ball to make it accelerate to the left. Okay? We're ignoring air resistance again. Okay? So there's actually no acceleration going on in the horizontal direction. So the acceleration in the x direction is equal to 0. So if I apply that to my first kinematics equation, okay, that tells me that V final in the x direction is equal to V initial in the x direction. That's weird. But all that is telling you is that whatever initial horizontal speed, velocity this object has when it leaves the table. So let's suppose it leaves the table with a velocity of 5 meters per second to the right, horizontally. It maintains that horizontal velocity throughout its entire trip. Okay? So when the ball is here, it's moving to the right at 5 meters per second. If I'm only looking at the horizontal motion. When it's here, it's still moving 5 meters per second to the right. When it lands, it's still moving 5 meters per second to the right. Okay? Now you might think, well, when it lands, doesn't it come to 0? It does, right? But that's only after it interacts with the ground and the force of the ground slows it down. Okay? If I'm talking about at the instant that it touches the ground before the ground has any chance to act on the ball, right? Its horizontal velocity is still 5 meters per second. And if I wanted to think about how far this object traveled horizontally, the distance traveled in the x direction, which would be this length right here, it has no acceleration, so this right term is gone. So it's just going to be v initial in the x, which doesn't change throughout the entire trip, times time. The horizontal motion is pretty simple to analyze. I haven't done anything new here. I've just applied the kinematics equation to the horizontal direction, and the horizontal direction doesn't have any acceleration, so it simplifies a lot. Now vertically, in the y direction, there is an acceleration. There's an acceleration due to gravity in the y direction pulling it down. And we already learned that that is negative 10 meters per second squared. If I wanted to know the final velocity in the y direction at any given moment along this path, I would have v initial in the y plus acceleration in the y, which is negative 10 meters per second squared times t. For this particular situation, this object, when it leaves the table, it has no initial velocity in the y direction. It's moving completely horizontally. So actually, this would simplify a little bit, and I wouldn't have this term, this initial velocity in the y, for this situation. I'm going to leave it because this is a special situation. It's the simplest case. If you actually did more like a football kick where you had a projectile that looked like this, you do have some component of the initial velocity of the kick in the y direction. So I'm not going to cut this out. I will leave it. But just remember that it can be removed if, for example, you're rolling off a flat table. You have no initial velocity in the y direction. And the distance that the object would travel in the y direction, which would be, for example, how far it has fallen, would be v initial in the y times t plus 1/2 acceleration in the y times t squared. Again, for this particular case where the ball is just simply rolling horizontally off the table, this first term is gone. So an interesting thing to think about is, would the time of flight change for whether an object is simply dropped straight down from a certain height, or whether an object has shot off the edge like that? And let's say they both fall the same distance. This one is dropped from rest. This one is shot off the edge straight. Which one do you think has the longer time of flight? Actually, both of them would be in flight at the same amount of time. The time of flight depends on the initial velocity in the y direction. And you can think about this. If you just kick a soccer ball straight, it has no initial velocity in the y direction, right? It's not like a football kick. If you just kick a soccer ball straight on the ground, it's not going to have any time of flight because it has no initial velocity in the y direction. If I throw a ball straight up, it's going to have maximum time of flight. So the time of flight depends upon the initial velocity in the y direction. Both of these have an initial velocity in the y direction of 0. So if you shot one of these out and dropped the other one at the same exact time, you would see that they would hit the ground at the same exact time. Google it. It's true. There's some YouTube videos that show this, and it's wild. Okay? So that's another thing to think about. What is this? So if I have a projectile, there's lots of different projectile types, right? I can have a really high projectile, but it doesn't go very far. Right? I can have a very, low projectile that goes a little bit further. What do all of these things, how can I determine what is the best, which one's going to be in the air the longest? Which one's going to have the longest range? And by range, I mean, how far is it going to go horizontally? Which one's going to go the highest? The height of the projectile depends upon the initial velocity in the y direction. Okay? The more initial velocity in the y that I give it, the higher it's going to go. Okay? If I throw the ball straight up, it's going to go higher than if I would have kicked it at the same velocity, but if I had kicked it completely horizontally. So that's one thing to take away. The time of flight. So hang time, how long is it going to be in the air? Also, we learned only depends upon the initial velocity in the y direction. If I kick it completely horizontally, I have no time of flight because I have no velocity in the y direction. If I kick it straight, if I throw it straight up, for example, I'm going to have a lot more time of flight. Now, range. How far does this go in the x direction? That's an interesting one, okay, because it depends upon the velocity in the, so we're looking at this one. It depends upon the time of flight and the velocity in the x direction. So for a really long, so if I have a really big t, if I have a really long time of flight, that means I have a really big initial velocity in the x direction, right? I'm practically throwing it straight up. But that means that I don't have a lot of velocity in the x direction or horizontal, so my velocity in the x is small. So it's not going to have enough velocity in the x to really go that far, even though it's in the air a long time. On the other hand, if I give it a really big initial velocity in the x, so a really low kick, I give it a lot of horizontal motion initially. So if the velocity in the x is really big, that means that the initial velocity in the y is really, really, really small. And that means that the time of flight is really, really small. So it seems like a conundrum here. How do I get a good range? How do I get this thing to go very far? You got to find the sweet spot, as I like to call it. The sweet spot is where you have a nice medium initial velocity in the x, which means you have a nice medium velocity in the y initially, which means you have a nice medium time of flight. Where does that medium actually occur? That occurs when you kick something or throw something at an angle of 45 degrees. So the range depends upon a couple of different things, the velocity initially in the x and the time of flight. The best range that you will ever have for a given, velocity that you're shooting this off at is going to be max range at 45 degrees. So this is a little quick crash course on kinematic equations, falling objects, objects under the influence of gravity, and projectile motion. And remember, in all of these cases, we have ignored the influence of air resistance. Okay. If you want, in the next chapter, I can talk a little bit more about the influence of air resistance because the next chapter is on forces. So Newton's laws, which explain motion, our laws of motion include telling us how forces cause the acceleration to happen in the first place. And so if we talk about forces, we can talk about things like the force of air resistance, air drag, frictional forces, and other things. But I just thought I'll give you a little quick crash course on this just to help you with your homework. Sometimes reading the book is really tricky, so having somebody explain it to you is always helpful too. If you have any questions or concerns, email me, stop by my office hours. We can always make an arrangement to meet on Zoom anytime if you need. I can often answer questions through email as well if it's a quick, easy question. So I hope this helped a little bit. And so this week you should be working on chapter 3. Next week we'll start on chapter 4. I'll see you. I hope you're doing well, and I'll see you next time.